if you'd like to come to Arundel Mills this Saturday from 11 to 12:30 in room 401. (11 to 12:30) Saturday, room 401 at Arundel Mills. I'm looking for optimization. I'm looking at the end of chapter 4. Any particular type of problem should I look for?
Marginal cost.
Ah. With the marginal cost. Oh, look at that, 57. It's also in red. 57 on page 334. Good point. Here it is. Let's read it together. If C of X is the cost of producing X units of a commodity, then the average cost per unit is C of X, small c, lowercase c, uppercase C over X. Show that if the average cost is a minimum, average cost per unit is a minimum, then the marginal cost equals the average cost. So that's part A. Let's see what they want in part B, because I think there is a part B up here. Yes. If C of X is 16,000 plus 200x plus 4x to 3/2, in dollars, of course, find the cost, average cost, and marginal cost of a production level of 1,000 units. So X equals 1,000. And we want to find the cost. That's not a problem. Cost of 1,000. We'll determine in a minute. Find the average cost. So remember, the average cost is lowercase c of x, which is uppercase C of x divided by x. And then the marginal cost at a production level. So then we are interested in finding C prime of 1,000. So this is the cost for 1,000 units. This is the average cost per unit. And this is the marginal cost at the production of 1,000 units, which, if you remember, it predicts the cost of 1,001 or 1,001st unit. And then minimize the average cost, and then and the minimum average cost. Okay. So let's do that. Is it okay if I skip finding C of 1,000 because we only have to plug it in? Is that okay? Okay. So let's look at the average cost. So lowercase c of x will be 16,000 plus 200x plus 4x to 3/2 divided by x. This is the average cost. Now let's find C prime, which is 200 plus 4 multiplied by 3/2 times x to 3/2 minus 1, which is 1/2. And this is 200 plus 6 square root of x. And then we have to find C prime of 1,000, which is 200 plus 6 the square root of 1,000. But now the interesting part is the production level that will minimize the average cost. Now, here's the average cost. Let's simplify it first, which is 16,000 over x plus 200 and plus 4, the square root of x. They want us to minimize this cost. Production level, it will minimize the, so find x that will minimize the average cost. We find C prime, not to be confused with this. So this is the uppercase, so I'm gonna do this so it's different. So this is negative 16,000 over x squared plus 4 times 1 over 2 the square root of x. Another ugly function, quite ugly. So this is the derivative of the average cost. Negative 16,000 over x squared plus 2 over the square root of x. And I have to find the least common denominator. Very ugly. Negative 16,000 the square root of x plus 2x squared. And now I have to set it equal to 0. And solve the equation 2x squared minus 16,000 the square root of x equals 0. Okay, not too bad if we move this to the other side and divide by 2. So x squared equals 8,000 the square root of x. And now we'll have to square both sides. X to the fourth equals 64 x. So one solution is 0. And then x cubed equals 64 million. And I take the cube root. So then this is 4, this is 0, and this is 0. It turned out to be very nice at the end. But it was an ugly situation. Units. And now I have to show that this gives a minimum. So the little c prime with 400 units and 0. I have to go back to the function. This is the function. And I'm going to plug in 1. When I plug in 1, this is 1, this is 1, this is 1, this is negative. When I plug in 1,000, that's why they asked us to find C prime of 1,000. Okay, when I plug in 1,000, this is positive, I won't bother with it. So when I plug in 1,000, this will be 2 million. And this will be less, right? So this is definitely will give us a minimum. So yes, we will say to the production manager, if you would like to minimize your costs, produce 400 units, whatever you're manufacturing, and make sure you sell them. Don't put them on the shelf because that's not going to work. And but in order to minimize your costs, just manufacture 400 units of whatever. So 0 is not feasible because we can't produce 0 and have cost. I mean, I guess we can, but it's not the purpose. Very good. Anything else? Other types of problems that you would like to go back to? Would you redo all tests for me several times? Will you come on Saturday if you have questions? Okay. What would you like me to do next? What type of problem? Limits. Yes.
Still kind of want to do more implicit differentiation.
Yes, of course, you mentioned that. I'm sorry, my apologies. Yes, sorry about that. Let's look at implicit differentiation. That is from chapter 3. Very good.
Something where you have to set the equation equal to y and then take the logarithmic.
Oh, so you want to determine the derivative of a function raised to a function.
Yeah.
Okay, very good. So let's create a function. We don't have to look. Let's come up with a function.
X to the y. I mean x to the z.
But we have to have a function that has only x. What about x to natural log x? You can change anything if you want to change. We can. Is this okay? Is it good enough? Okay, so see what happens now. I have to apply natural log, and then I get natural log x times natural log x. So when we apply natural log to the left-hand side, we get natural log y. When we bring down natural log, I have natural log times natural log, which is okay. It's natural log x and everything squared. So then, when I differentiate the left-hand side, I have 1 over y, dy over dx. When I differentiate the right-hand side, I have 2 natural log x times 1 over x. It was kind of easy. So now dy over dx equals y multiplied by, I can put 2 in front, natural log x over x. And I have to replace y. dy over dx equals x with 2 in front, 2x raised to natural log x multiplied by natural log x over x. And I think we should choose another. What about 49 on page 223? The tangent raised to 1 over x. I'm pretty sure we did this one too. If you want to change anything, we can. If you want to change tangent into something else, if you want to change 1 over x into something else. No? Okay then. So then we have natural log y equals 1 over x times natural log applied to tangent x. And now we can differentiate both sides. 1 over y times dy over dx equals product rule, negative 1 over x squared natural log applied to tangent x, and plus 1 over x times 1 over tangent x times secant squared x. Is this okay? Is it okay? So all I have to do now is just write dy over dx multiplied by y, but y is this function. So I write tangent x raised to 1 over x, and then in brackets, yes, you can factor out 1 over x if you want to, no need. natural log of tangent x over x squared plus secant squared x over x tangent x. And you do not need to do anything else. Any other topic or type of problem? Anything else? Anything else? I recommend coming early on Tuesday if you have, just in case you have more questions or you think you need more time. I will post the videos from Saturday as well. In both classes I teach.